So for number 6, we're looking at the area outside of r equals 2 sine of theta and inside of r equals 4. All right, so it's pretty straightforward if you have the diagram. So what I did was I just put the diagram on Desmos. I left it in rectangular form. You could see the Desmos version of it in polar form. Either way is fine. So what I'm going to do is find the area in between those two by finding the area within the blue circle followed by the area within the red circle. So each one of these integrals represents an area model. Remember the area formula on the interval of a to b or alpha to beta, we're looking at 1/2 r squared d theta. All right, so we have an r value of 4 for the first circle and an r value of 2 sine of theta for the second circle. All right, so really it's just a matter of integrating these two functions. The question is, well, where do the bounds come from? So the bounds for the larger circle, that's an ordinary circle centered at the pole, those have a domain of 0 to 2 pi. And we learned in previous examples that a circle in the form of a sine of theta or a cosine of theta has a domain of 0 to pi. All right? So it's really at this point that we can just carry through the process, because once we find our integrals, we can subtract the two and we'll have the area in between the two circles. All right. So the solution for the integral in blue is actually pretty simple because it's constant. So 1/2 4 squared is 16, half of which is 8. The antiderivative of 8 with respect to theta is going to be 8 theta over the interval of 0 to 2 pi is going to give us a 16 pi. So that part should be fine. But then for the other one, we're integrating a sine squared essentially. So what we'd have to do is clean it up. We can square the 2 sine theta, making it 4 sine squared theta, but then the 4 multiplied by 1/2 would be equal to 2. But then we'd have to perform a substitution on the sine squared theta, replacing that with a 1 minus cosine 2 theta over 2. All right, so that's old school Calc 2. It's just a trig identity replacement, right? Which allows us to clean things up a little bit, which is good because then we can integrate a simpler expression, which is 1 minus cosine 2 theta. This is all assuming you want to do it by hand. You can just pop it into Desmos if you want. All right. When we integrate, what we're looking at, I'm kind of stealing my own thunder here. Let me do it this way. We're looking at theta minus the 1/2 sine of 2 theta, because I always operate under the assumption whenever you have a trig function, you're really just, when you're integrating, you're kind of treating it as if the constant multiple isn't there. So the antiderivative of cosine 2 theta, well, forget about the 2 for a sec. Antiderivative of cosine would be sine. So you'd say, okay, well, I suppose the antiderivative is sine 2 theta, but then when you take the derivative of sine 2 theta, you get cosine of 2 theta times 2, which is double what you want, so we throw a 1/2 in the front to correct for that. All right, so then what we do, there we go, is after we integrate, we pop in our bounds, and you see that it simplifies down to pi. So we have a 16 pi for the outer circle, pi for the inner circle, and that brings us to our overall conclusion, which is the area outside the one circle and inside the other, 16 pi minus pi is going to be equal to 15 pi. And so that would be your complete solution. All right, by comparison, arc length is a little bit simpler. All right, so at least procedurally. So on page 7, number 7, we're looking to find the arc length on the indicated interval. So what I'll do is I'll open a fresh new Desmos, which is r equals 7 times the sine of theta, Sometimes my fat fingers get me in trouble. All right, 7 sine of theta over the interval of 0 to pi over 2. All right, so that's a semicircle. We ought to be able to figure that out using conventional techniques. All right, but they give us the start and the stop in terms of theta. All right, so we know we're going over the interval of 0 to pi over 2. We have r. So 7 sine of theta. We're going to square that. Plus the derivative, so I'll just write it as r prime right here, is going to be 7 cosine of theta. Quantity squared. Tack a d theta on at the end. Let's smidge this over. Maybe shrink it down. And this one I think is easy enough to do by hand, because we're going to have 49 sine squared plus 49 cosine squared under the radical d theta. Factor out the 49. Radical 49 becomes 7. And we're left with the square root of sine squared plus cosine squared. Sine squared plus cosine squared is equal to 1. So square root of 1 is 1. So we're looking for 7 times the integral of 1 d theta. So 7 theta over the interval of 0 to pi over 2, which is going to be 7 pi over 2. Looking at number 8 on page 7, we have r equals 3 times the secant of theta, so we can just pop that in. R equals 3 secant of theta. And again, I just find that the quickest way to get the theta in there is just type it. All right, you see that's a vertical line. We can go through all the processes to verify that by converting over into rectangular form, but at this point, since we have a formula that'll give us an arc length using polar coordinates, why not just leave it as is? All right, the domain that we're concerned with is pi over 4. All right, so we're only looking for that little segment. Now that segment seems to be 3 units long. All right, so that's kind of what I'm going into this problem with in terms of the mindset. All right, so let's take a look. We're going from 0 to pi over 4. And d theta at the end. I'll write r prime instead of the r d theta. Secant of theta has a derivative of secant theta tangent theta, so 3 secant theta tangent theta. All right, so we're looking at 3 secant theta, quantity squared, plus 3 secant theta tangent theta, also squared. All right, so we have a common factor that can be pulled out. Now, this is assuming you want to do this by hand. Right? So I'm just kind of operating under that assumption. So we have a common 3 secant theta squared that could be pulled out. All right? So 3 secant theta squared times 1 plus tangent theta squared. Squared. Under the radical with a d theta with our bounds. All right. So we just pulled out a GCF. Now we could pull it out further and make it 3, for quality 3, secant theta and then we would still have the 1 plus tangent squared theta d theta. All right, so it was the tangent that was squared, so I guess I could have put it like that in the previous step. All right, so now it's like, okay, well, what do we do? Do we go to the calculator? Well, we could have done that from, the word go. All right, now I just want to remind you of something. Good old Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. But then what if we divided each of these terms by cosine squared? If you did, then you would get another variation of this. Tangent squared theta plus 1 is equal to secant squared theta. All right, so it actually cleans up rather nicely. 3 secant theta. And honestly, the only reason why I'm going through this by using a by hand approach is because I looked at the picture and I saw it's going to end up being relatively clean. And if it's not, it's going to be very close to relatively clean. Then I'm thinking that maybe I got a shot in the dark of getting a nice simple kind of approach, or solution, I should say. All right, square root of secant squared is secant, so we're looking at 3 secant squared theta over the interval of 0 to pi over 2. Oh, somehow my pi over 4s became pi over 2s. Apologies. The whole walking and chewing gum at the same time thing. D theta. The antiderivative of secant squared is tangent, so 3 tangent theta over the interval of 0 to pi over 4, which gives us 3 tangent of pi over 4 minus 3 tangent of 0. Tangent of 0 is 0. Tangent of pi over 4 is 1. So 3 times 1 minus 3 times 0 is just going to be a 3. All right? Which is consistent with the length of that quote-unquote arc. When you're talking about arc length of something that is a straight line, you're just talking about the length of that line.